Let's now actually construct free products. This is quite similar to constructing free groups, so we'll be quite sketchy. So remember, the data is not the product but a family of groups, J alpha, alpha in A. And as with free groups, we'll look at words, and they may be empty words, G1, Gn. Okay. In the case of free groups, these were in generators and their inverses, but here they are in some groups. There exists alpha n such that there are indices such that Gi is in G of alpha I. By the way, we'll assume that the groups are disjoint as sets. So every element is in a unique G alpha. You can do some set theory trick to ensure this is the case. Okay. And then we have a multiplication, which is again concatenation. So I should clarify here. Let me emphasize. When it was implicit, it was ambiguous, n greater than or equal to 0. So the empty word is allowed, and that will be the identity as before. So G1, G2, Gn star, if I look at G1 prime, Gm prime, this is just, of course, the concatenation. By the way, in practice, we don't write them as tuples, we just write them as words. But since this is the first time many of you would be seeing them, I'll be more formal and I'll write them as words. Okay, so far so good. And of course, we want an equivalence relation. So tilde on W generated by. Well, what do we need here? Well, it's a little bit different from the previous case where we simply cancelled letters and their inverses sitting next to each other. But our first move is similar to that. Okay, namely, if alpha I is alpha I plus 1, that is, the two adjacent letters are in the same group. Okay, so the two adjacent indices are the same, then G1, G2, Gi plus 1, and so on to Gn. This word is equivalent to the word where I merge these two. So to emphasize, let's see Gi minus 1, and then I have Gi plus 1. Okay, and then we have Gi plus 2, and so on up to Gn. So this is a word which is one step shorter. This takes care of things. But by the way, this still doesn't allow cancellation. What if Gi and Gi plus 1 are inverses of each other? Well, we have another move for that. Namely, if Gi is the identity, of course, in G alpha I. Okay, so there are lots of identities. Then we can simply delete it. Okay, so G1, G2, Gi and Gn. I won't write the previous words. Is equivalent to G1. Just go up to Gi minus 1. Sorry. So this is equal to E. I could have just written it in this shorter form. Gi minus 1, Gi plus 1, Gn. Okay. So that is, I could simply write it as G1, G2, Gi minus 1, E, Gi plus 1, Gn is going to be equivalent to G1, Gi minus 1, Gi plus 1. A special case of this is if you have a single letter and that letter is identity, you can just delete it and you get the empty word. No problem here. Okay, and then we can easily see that this actually, so star induces an operation, a multiplication on W by tilde. If two words are equivalent and we concatenate them, we'll still get equivalent words in the two pairs of words. That's very similar to the case of free groups and is straightforward anyway. Okay, so let's define our group and then we'll see a couple of properties of it. So you let star alpha, J alpha, alpha in A, be by definition equal to W by tilde, and I alpha, which will map G alpha to star of alpha in A of G alpha, be the obvious map which will send an element here to the single letter word, which is G itself. Okay, so here we have a map, and it's easy to, well, by the way, why is this a homomorphism? Okay, so that's not so trivial, it's not difficult, but it nicely illustrates the equivalence relation. So you remark, if I look at I alpha of G and multiply it by I alpha of, let's say, G prime, okay, which is another letter. Well, what is this? This is G star G prime, okay, but more precisely the class of this, so indeed I should say class of this letter here, which is the class of the pair G G prime, but remember that is equivalent to G G prime, a single element G G prime, because I can merge things if they lie in the same index, and G and G prime both lie with the same index alpha, and this is I alpha of G star G prime, where here you have multiplication in the group G alpha. Okay, while this was elementary, it nicely illustrated that how the equivalence relation allowed things to behave well, in this particular case being a homomorphism. Indeed, that's what we'll see next. We'll similarly see how we have inverses to make this into a group, and we'll see how we have the universal property. Both these will be elementary, but they will also illustrate the equivalence relation, so we'll see them in a little detail. So let's see that it's a group and universal property. E is the empty tuple, which is can write like this. E is the identity. E is an identity, hence the identity. Okay. Already W is a monoid with this as the identity, and we want to see that we have inverses. So namely G1. If I look at G1, G2, Gn, each Gi belongs to different group in general. They may or may not be different. Has inverse. So let me be precise and say the class of this tuple has inverse. The class of, well, you can guess, of course, what it is. Gn inverse all the way to G1 inverse. But why is this the case? As if I look at the product of these two, G1, Gn, multiplied by Gn inverse, G1 inverse, okay, this is the class of G1 all the way up to Gn, and then we have Gn inverse, etc. up to G1, and the rest will be very similar. But the key point is that notice that this is in G alpha n, and so is this. So we can merge them. So it becomes G1 and then Gn inverse onto G1. Sorry, the last one is a G1 inverse. And this is E. And so we can delete it. G1. This is the identity of the appropriate group. So Gn minus 1. Gn minus 1 inverse. G1 inverse. Okay. So rest by induction. Finally, you'll end up with a letter and its inverse, which you cancel, as we see. That last part is more or less like the proof of homomorphism. So this illustrates where the result comes in. And finally, as far as the universal property is concerned, that is, we are given the data. So we are given H. So what are we are given H, and we are given phi alpha. This is going to map G alpha to H. Okay. So define, let's call it phi tilde, mapping the words to H by phi tilde of G1 Gn. More precisely, phi tilde of the tuple G1 G2 Gn is going to be phi alpha 1 of G1 multiplied by, this is the product in H, so on up to phi alpha n of Gn. So we have a natural map. Okay, so this induces phi. This is going to map the star alpha in A of G alpha to H. So it's routine to see that if I have two equivalent elements, then the right hand side will be equivalent. It's worth seeing this as an exercise. That is, if I have gi and gi plus 1 from the same group, if I merge them, the homomorphism property of phi alpha I is what will give me the result. And the other thing we can see is this induces phi from these, and this is unique. Or I should rather say this uniquely satisfies for all alpha in A. We have G alpha, which maps to we have the inclusion map I alpha, the star alpha in A of G alpha, and H, this thing, phi alpha commutes. Okay, so this is the summary. I mean, so again you'll have to check. So the thing is that if I have n letter word, since it's the product of single letter words, the phi has to be forced to be equal to the value on the single letter words, and on the single letter words the commutative diagram determines phi alpha. So this is the unique definition, and the single letter words this diagram commutes will tell you that it commutes on all words, and that is the proof that the universal property is satisfied. So some details have been skipped here, but they are not difficult and they are very similar to those in the case of free groups. Okay, so with this algebraic thing behind, we will see our first part of Seifert-Weinkampen theorem and then come back to a categorical view briefly.